some announcements before we start class. So I suppose as far as due dates go, as hopefully you're all aware by my notification, the quiz was due, well, last night. And so we move on to assignments pertaining to normal distribution. So we started talking about normal distribution last time. We're going to talk about it more today, a little bit more next class period as well. There is a homework due tonight on the normal distribution, the very first homework, but this is a very definition-based homework. You can knock this out. In fact, half of you have already knocked this homework out. So please get this homework done. This one's a very quick one. You can get that one knocked out in no time. Mainly, the focus is to get that one out of the way so we can look at the next homework assignment, which is normal distribution applications, which we're going to talk about more today. That involves the table that we've been using, determining the area under the curve in different situations. That homework, I have it set for Wednesday for now. And so I have the next few assignment due dates already put in here. And there's not too much flexibility with these due dates moving forward because our next exam is not this coming Wednesday. So it's not next Wednesday, but the following Wednesday. That is our next exam, the following Wednesday. And so the plan is to get up through normality, maybe cover a little bit of distribution of sample means, which is in chapter 8. If not, that's not a big deal, but that's ultimately the plan moving forward. Additionally, as you'll probably start to hear from all of your professors, the withdrawal date is this coming Friday at, I believe, noon. So if you are going to withdraw from any class, not just this one, or considering withdrawing, the latest you will have to do so is Friday at noon. Besides for that, I believe that's all I have. So does anyone have any questions for me before we get started? If not, let's go ahead and pick up where we left off. Okay, so last time I ran out of time on example 3, but ultimately what we were talking about was finding the area under the curve in standard normal situations for standard normal variables. And an interesting assumption we get to make about standard normal variables is that the mean is 0 and the standard deviation is 1. And how that helps us is we've been using this very helpful table in the back of the notes. So if you don't have the notes printed out, if anything, you definitely need this as a reference, these 2 pages in its entirety. This will help you with the homework for 7-2. But you definitely need these 2 pages. And what we talked about last time in class was how to read this table. And what we're going to be talking about today in class is more of reading this table and just the different situations that might occur. So as I mentioned, we were on example 3 here, and I'm just going to go ahead and restart the problem just to get everybody on the same page. So we're trying to find the z-scores that separate the middle 16% of the distribution. And so the object, the visualization in mind for not only this section, but this whole chapter was normal distributions, which implies a normal curve. So we've been looking at these normal curves. In fact, there's some illustrated right above. But ultimately, this is the thing we've been looking at. And with these, now this gives us an understanding of maybe how to format everything. Now, the middle 16% is ultimately 2 regions that, well, we always have a mean. And in fact, we know exactly what that mean is because we have a standard normal distribution. The mean is always 0. Again, like I said before, the mean in a standard normal distribution is always 0. Again, this is mainly helpful so we can use that table in the back of the book. But more so, if we want to visualize the idea of selecting the middle 16% of the data, well, the middle 16%, well, we have that line right in the middle, that nice divider. We go 8% one way, 8% the other way. So 8% one way, 8% the other way. It doesn't have to be perfect. So let's just say that this region is the middle 16%. And this curve, this normal curve, is perfectly symmetric. So we do know that, well, if anything, it might help us knowing that it's 8% on one side, 8% on the other side. But I'll make that clear that the area is, it's not 16. The area is not just 16, it's 0.16. They gave us a percentage. We view percentages in this class as a proportion, which makes sense because the area under the curve is 1. 16% of 1 is 0.16. So ultimately what we're trying to do, we're trying to find the z-scores. Now the z-scores just represent these blue boundaries here that I wrote. So this would be a z-score, which I normally call z0, z with a little 0 next to it. And then z1 for the second one. There's a lower boundary, an upper boundary. Well, guess what? We're going to find both of them. So what we know is that we have a table in the back of the book, or well, the back of the notes as well. And that table can be used for whenever we have any values going to the left of the z-score. So right now, all we have really is a situation where we have a variable stuck in between two z-scores. So what we can do, one thing we can do is figure out both of these areas separately, break them down separately, and then either add or subtract in a particular way to where we can get what the z-scores are. Or ultimately, we're working backwards, though, because we know the area is 0.16. So we can honestly do this in a number of ways. We do this in a number of ways. But the problem is, if we took that area of 0.16 and tried to go down to the table, so if we tried to go down to this table here and tried to find 0.16 in terms of the areas, which are these values, those areas only correspond to the left of a z-score. We don't have any of those situations, just the pure left of the z-score all the way to the end. So we need to manipulate the graph to get a situation like that. So one way we can do that, we have the graph already. Instead of looking at the inner, instead of looking at the inner 16%, we can look at the outer remaining percentages, or the outer proportion, which I'm highlighting now. So instead of the inner 16, we look at the outer, whatever the area is for this one, the complement, in other words. Because now with that outer, the complement of the area, now we have situations where we have less than a value, greater than a value, and we can use the table. So we wouldn't have to do this, except we have to put it in a format to where we can transcribe it directly to the table. So what would the area of these black shaded regions be? It's the area of the black shaded regions. That's plural, so cumulative. What's the... What's that? 0.84. It's 0.84. So we had 0.16 from before, but we're subtracting that from 1 because we're intentionally finding the complement. We're finding everything else. And that's 0.84. So we know that both of these regions added together accumulates to 0.84. Well, the problem is we only want to deal with one at a time. So guess what we do now? Take the 0.84 and instead of looking at both areas, we want to look at just one area. Maybe this one on the left. So we have one more thing we have to do. Divide by 2, of course. Divide by 2 because they're symmetric. And that's 0.42. So this is the area. Now the situation is, so the part I circled in the notes, the area that I circled is 0.42. So the area of that is 0.42. And now we can use that information to find the first z-score, which I call z0. Again, it doesn't matter if you call it z1 and z2. It's just computer science lingo. But so we have 0.42. And so all we have to do is go to our table, use this area, and then find the corresponding z-score. Let's take that area, 0.42, and I'm going to just keep reading the rows until I get closer and closer to 0.42. Remember, I'm not looking at the z-score parts. I'm not looking at the first column. I'm looking at these values all around here, because those are the areas. So 0.42, the closest one to 0.42 is right here. That is the closest value. Now, some of these round up to 0.42. So this value right here does round up to 0.42, but the one I circled is only 7 units away from 0.42 perfectly. The one I underlined is 32 or 0.0032 units away. Or in other words, the one I circled is, again, the closest one to 0.42. So we have to figure out what z-score that corresponds to. Well, just like we did in class before, the first 2 digits, it's negative 0.2, and then we scroll up to see what the hundredths place is. So it's really negative 0.2. That's it. That is the z-score, negative 0.2. Negative 0.2. So we have one of them. And now we have to figure out the other one. Now, there's actually 2 ways in which we can figure out the other one. Does anyone happen to see what the other one is already, by any chance? Anyone want to give it a shot? It's positive 0.2. So why is it positive 0.2? Well, remember what I said earlier about with the middle 16% of the data, 8% one side, 8% the other side. The mean is 0. So 8% to the left, let's see, to your left, that'd be this way. So 8% meant you got, well, because you're going less than 0, you're getting a negative. And what's the magnitude? 0.2. But if you're going the other direction with the same amount of magnitude, you're just getting the positive version. So it's negative 0.2 on one side, positive 0.2 on the other side, because we're utilizing this symmetry. Now, if you did not see this, then you might have to do a little bit extra work, because the area would still be 0.42. So this area would still be 0.42, but you can't use the table because the shaded in region's on the right and not on the left. So then you'd have to find the complement of 0.42, which is 0.58. And then you could use the table. And just to verify that, 0.58, let's now utilize the table. And the closest one to 0.58, so really 0.58 would be right in between these two. This one is 1000. Yeah, this one is 0.0007 from 0.58. This one's 0.0032 from it. So this one is absolutely the closest. And then notice what that corresponds to, 0.2. So that's two ways you could do it. Either utilize the symmetry or you could just work it out normally. But you do have to complement because this only works to the left of the z-score. If you're not looking at to the left of the z-score with no obstructions when you go to the left, this table is useless to you. So you have to manipulate the situation to make this something you are looking at. So we found the two z-scores, and that's all we had to answer for this problem. So the answers being negative 0.2 and positive 0.2. Does anyone have any questions about this before we move on? We'll see a problem like this again. So in case you might have missed that one, we're going to look at something fairly similar in the future. If not, let's move on to example 4. Now, there's a shorthand that we'll be using as this class progresses, and it's a z with a subscript, which I have defined loosely in this class before as meaning the z-score corresponding to this or that. But moving forward, what this notation represents is, well, it represents the z-score such that the area is whatever the subscript is. So it's saying what it's saying is that the area to the right, not to the left, to the right, is 0.39. That's what it's saying. So it's not saying that the z-score is 0.39. It's saying that the area is 0.39. And so we need to find the z-score because it's z set equal to something. So that makes sense. We're trying to find a z-score. Well, again, anything involving the area to the right is not going to help us in terms of the table because the table only works when we're looking at area to the left. So if the area to the right is 0.39, the area to the left is, what's that?
Negative 0.39.
So not negative 0.3. Remember, we don't have negative area. I think you might be getting z-scores in area. Yeah, it doesn't help that they're the same types of values. They're both like very small values. The area to the right is 0.39. Think about this as a visualization. Area to the right. So let's just say the area to the right is 0.39. And what's the area to the left? Yeah, it's 0.61. So maybe that illustration might be helpful. So in fact, I could just carry this on in this logical definition, which normally when you see 3 lines, not an equal sign, but 3 lines, that means a logical equivalence. So the logical equivalent would be area to the left is 1 minus 0.39, which is 0.61. And so now we can just use the table because we have to get that left part in. We don't have left, it says right, we can't use the table, and we have to manipulate the problem. So 0.61 is what we can go and bring to the table. So 0.61, go to the table. .61. So 0.61 is going to fall between one of those two values. Now, definitely the one closest to 0.61 is this one right here. It's only 3/10,000ths off from 0.61. The other one is much further off, relatively speaking. And when it comes to MyMathLab being very picky about these, it wouldn't let me increase the margin of error in case you did in fact pick this one on the left. So you have to be very picky, or very careful about picking the one that is as close to your area or z-score as, well, mainly area, it doesn't really apply to z-scores, as close to the area as possible. And if you do have any issues with the nitpicking over a 10,000th of a decimal place, just let me know and I'll give you your points back. That's not a big deal. I can do that very easily. So we're looking for z-scores. Simply move over here, and the z-score is 0.28. That's it. That's how that notation is applied, which we will be utilizing moving forward. So the z-score is 0.28. So it's now equal to, not logically equal to, it's just equal to 0.028. That is the z-score that corresponds to an area of 0.39 to the right of the z-score. Does anyone have any questions before we move on? If not, we have been utilizing something very helpful here, this idea of standard normal. We haven't really been touching normal distributions. We've been looking at standard normal. I think, well, what's the difference? Just one word? Well, there's a huge difference, because standard normal, you get to assume that the mean is 0, the standard deviation is 1, and you get to use the table in the back of the book or the back of the notes. If you just have a normal distribution, you cannot immediately do that. Normal and standard normal are not the same thing. Standard normal is a formulative transition of normal. And how is this transition done? Via the formula I gave at the very beginning of this section, which we haven't really touched, but we're going to look at for the remainder of this section. And this should look familiar because this is the z-score formula. It's just, instead of lowercase z and lowercase x, it's uppercase to represent random variables now. But it has the same purpose. But this also introduces a little bit of symbolism. So in example 5, we're not assuming standard normal, we're assuming normal. And notice the mean is not 0, the standard deviation is not 1. And what we're going to do is just see, how does this affect things? Because in its current form, we cannot use the table. So additionally, we do switch to notation that involves things formatted as such. And I'll explain as well what this corresponds to. It should be pretty straightforward. But what we're going to start off doing, let's go ahead and just think about and construct the illustration so we can see what this notation means, what does normal distribution mean without standard normal, and how to go about it. Well, in any bell curve, there's always a mean right smack in the middle. They tell us the mean is 25 though. They just tell us that in the problem. It's not standard normal, so the mean is not 0 anymore. Now, the specific number that they gave us here is 19.5. So 19.5, I'm just going to say that falls right over here. It's not really it's not a z-score or anything. It's just a value in consideration. And of course, it's less than 25, so we'll put it to the left. Additionally, it's saying since x is greater than this, when they use, so really another sort of implicit thing that's happening here is that we're not using the word area anymore, and we're going to use the word probability. But one of the axioms that we learned about in the previous section is that the area and the probability are equivalent. So in other words, we're still looking for the area that is whenever x is greater than 19.5. This is the area when x is greater than 19.5. Because there's 19.5 over here on the left. Just go directly to the right of that because it says x is greater than that. So the area and the probability mean the same thing in this section. It's just to find the probability, we use the convenience of an illustration, i.e. the area, to find this. And this is the illustration. That's all there is to it. That's the illustration. Again, it's putting down the mean, putting down the point or points in question, and then just following the inequality symbol. It's as simple as that. But now we need to compute the probability. And so to compute the probability, which I'm just going to rewrite over here, we need to figure out the area of the shaded region, which we have been doing before. But we need to, in order to use the table in the back of the book, we need to convert any normal values into standard normal values. In other words, we need to take any data value or values in question and convert them to a z-score. How do you convert anything to a z-score? You take the number that you want to convert, you subtract by the mean, and you divide by the standard deviation. This is the z-score. Again, this is a formula that I gave a decent while back, and I'll write it on the left of the screen. That's the formula I'm using, and applying it is happening over here on the right. $19.5 minus 25. So you always subtract. You don't add. You subtract. If you figure that out, then you divide by the standard deviation. And since this is a z-score, in the back of the book, the z-scores only go to the hundredth place. You have to round to the nearest hundredth. And that's what I get, provided you typed it in your calculator correctly. And again, this is because in the back of the book, the z-scores have a ones place, a tenths place, and a hundredths place only. So that's all we can utilize with this information. So what this tells us now is instead of looking at the probability of when x is greater than 19.5, we are now going to look at the probability of when z, capital Z, that's a capital Z, is greater than negative 1.57. Because what we did, we converted from normal, which was x, to standard normal, which is z, which means a slightly different notation, but it basically means we're not looking at the data value as a value, but we're looking at it as a z-score, which means we have just transformed, we've we've implicitly changed the types of values we're looking at. In statistics, we want to normalize values to be in a very certain confined space. And if you want the layman's way of saying it, by looking at it as a z-score, now we can use the table in the back of the book. That's the only reason why we did this. And the only reason why we did this is because it said normally distributed instead of standard normally. If it said standard normal, we could just use the back of the book, no problem. But it says normal. You have to convert it. Now we can use the back of the book. So the problem is the back of the book is going to give us the area to the left. But this, I mean, the shaded region is very clear. We're wanting the value to the right. So what we truly want that will be incredibly helpful is 1 minus the probability of whenever we find the complement of the inequality. So notice it was a z is greater than, because it originally has us finding the area greater than the z-score, but we're finding the complement just so we can look at the area to the left. That means we can use the table, because the table involves us looking at values to the left. So notice everything we're doing is just so we can satisfy the table, the conditions or the prerequisites for what it means to use the table. We have to have z-scores. We have to look at values to the left. Now we've accomplished both. Now it turns out the equal to sign doesn't do anything in this whole chapter. The equal to sign does not change anything. The probability at a specific number is always 0 for reasons we don't get into in this class. So we're going to treat it as if it were a less than or equal to sign or just a less than sign. It does not change anything. We'll actually see that in problem 2 at the bottom here as well. So basically that's it. We know the z-score, negative 1.57. Let's go find the area. So negative 1.57, there's negative 1.5, which gives us all of these values in this row. And then here's 7 right here. And the overlap between the two, 0.0582. 0.0582. 0.0582. .0582. And notice I'm putting it as 1 minus because we found the area that corresponded to the left, but our context, we know that we found the complement, and then all we have to do is subtract that from 1 to get the final answer. And that is the final answer. So this is the transition we go through, along with some other stuff we've talked about before. But this is ultimately what we go through whenever we're given a normally distributed situation. We have to standard normalize it, or standardize it, in more concise terms. And then we can use all the resources, provided we manipulate the problem in a certain way. Does anyone have any questions up to this point? If not, let's scroll down to example 6. We have a few more problems, fairly similar. So again, this is a normal distribution, not a standard normal. And they go on to tell us that the mean and the standard deviation are not 0 and 1 respectively, which immediately gives us some insight on how we can fill in these graphs. So let's go ahead and illustrate these for each given situation. I'll start with the left one. 75 less than x less than 106. So with this problem, let's see, so 75 is of course less than 90. So it's going to go over here somewhere. Again, doesn't have to be perfect. Just some way to let us know that, all right, 75 goes there. Right, just to make it look a little bit nicer. I'll just do it down here. And it doesn't matter. And then 106 is, of course, larger than 90. So we can go ahead and put that over here somewhere. Now, of course, this is not going to be symmetric on both sides. The difference between 90 and 75 is different than the difference between 90 and 106. But again, it doesn't matter. Just something to illustrate, to give us an idea of what we're looking for. And since this says x is sandwiched in between those two values, well, then we're looking for this area, right in the middle. That's what we're looking for. We want that area, because that area will correspond to the probability that we want. The problem is the values we have are not standardized because we have a normal distribution, which means at the minimum, the chart in the back of the book will not be helpful. As far as we're concerned, that is the only way in which we can find specific areas. So for each one of these values, so these are not z-scores, so I'm going to call them x0 and x1, because they're not z-scores. Again, they're next to a capital X. But I'm going to find the z-scores for each one of these. So we'll start off with the first z-score. Well, the first x value is 75. We have to subtract off the mean, which was 90. And then divide by the standard deviation, which is 28. And that's how you standardize an x value. I'm going to carefully round it to 2 decimal places, because that's the that corresponds to as much information in the table in the back of the notes. Negative 0.54. That's the first z-score. Second z-score, same thing. So its value was 106. Still subtract the mean. Still divide by the standard deviation. Changes ever so slightly. 106 minus 90 divided by 28. 0.57. And that's another indication that we do not have a symmetric spread of these z-scores. It's not the middle symmetric percentage of the values. It's not the same distance from the mean in both directions. One is slightly further to the right in particular than the other one is to the left from the mean. And so from here, now we know, well, the z-scores. So instead of looking at the probability of 75 less than x less than 106, we can instead look at the probability of negative 0.54 less than z less than 0.57. Because we've standardized everything. Now the question remains, well, how do we use the table now? So the way we use the table, well, we can look at we could technically look at the opposites, like we did for that first problem when we started class today, or we can try something else. If we find the area for the z-score that corresponded to 106, and that area would be all of this. That's what the table would tell us. it would give us that red shaded region. But that's way too much information. Of course, there's the z-score still there. So if we found the area for the 106, then that's the area it would give us. And I'm going to write that one down first, and just hang tight with me for now. So this is the area corresponding to the 0.57, because that's what the 106 converted to. So the 0.57 is the z-score. We need to find the area corresponding to that z-score. So 0.57. So here's 0.5. And here's 7. 0.7157. 7157. That's not the answer, though, because, well, one, we didn't do anything with the other value. So if we wanted to trim off the excess part here, and I think everyone can agree that this part I'm shading in blue right now is the excess part, and how would we have to apply that area in blue to the area I just wrote down? I have to subtract it off. Subtract it off. Because we had too much area, so then we need to subtract the excess. So in other words, we're trying to find now the area of negative 0.54. Negative 0.54. Here's negative 0.5. So 1, 2, 3, 4. It would be right here. It's 0.2946. 0.2946. That difference will give us the answer. .4211. Okay, so that's, and so ultimately what we're utilizing here, so this isn't the answer to the next one, but I want to motivate where this is coming from. Negative 0.54 less than z less than 0.57. There's one inequality here, which is z is greater than negative 0.54, and the other one is z is less than 0.57. This one we can find really easily on the table because it's less than. You can just use the table. But the other one you can't, which means you have to use its complement. So maybe not 1 minus, but the complement, as we talked about already, was z is less than or equal to negative 0.54, which means you would end up subtracting. That's why this one was the subtraction one and this one was the addition one. And so that's kind of the motivation why we found this one first, then we found this one second and had to subtract the second one from the first one. So that is the motivation for why I chose these values in this way. We're going to do one that's 100% similar to this. So in case you might have missed that, let's go ahead and look at problem 2, and then I'll ask if anyone has any questions. Same idea. In fact, same process. The only aesthetic difference is that there's an equal to part right here. That's the only difference. And it turns out in this section, well, actually in this whole chapter, anytime we deal with continuous variables, the equal to doesn't mean anything here. We can take it off, we can throw it back on. It doesn't mean anything. We mentioned at the very beginning of this chapter that the probability of at a specific number is always 0. So that means if we tack on the extra 138 at the end by putting the equal to sign, it doesn't change anything. So we're not going to treat this problem any different than the last one. So we could start off by illustrating what we're looking for. 114 is, of course, larger than 90, and so is 138. So actually, we're looking for a region that's over here. 114, 138. And so we're finding the region in the middle here. So that's what we're trying to find. In order to use the table, though, we need to convert those values into z-scores. So the first one was 114. The mean is still 90, still have the same assumptions, divided by 28. And we can expect both of these z-scores to be positive because both of these values are larger than the mean. .86 for one of them. And we can try to fit the other z-score in here as well. 138 minus 90 over 28. .7. Okay. We have our z-scores. Let's go ahead and look at the problem as now 0.86 is less than z, which is really just less than. Again, you could put the equal to sign if you want. It doesn't change anything in this problem. So notice I'm using a capital Z now, though, because we standardized. And so yet again, we need to look at, again, I'll write it out a little bit more explicitly here. Z is less than 1.71 minus the probability of Z is less than or equal to 0.86. That second part is the complement that I'm already addressing. Again, the equal to part is merely the complement of the inequality, but it doesn't change anything at all. But this is just the intermediate step that I didn't write in the previous problem. So what we do is, well, just find the areas in the back of the book. So 1.71, that's the first z-score. So let's go find that one. .7 is about right here. And 71. 0.9564, that seems to be the first one. 0.71, so 0.9564. 0.9564. And then that minus, just find the area for 0.86. Zero 0.86, 0.8. Here's 6. So that's 0.8051. 0.8051. find their difference, and we're done. 9564 minus 0.805. Oops, check that out. 9564 8051. And we are done. 1513. And we're done.
How did you get point that the z-score is on the second one it was less than, less than 0.86, but above it you have it's I'm just looking at it wrong, I'm sorry.
So I switched the z-scores, the order of the z-scores, because I wanted the larger value to go first. So are you asking why 0.086 became 0.171 and why 0.71 was this? Is that what you're asking?
Yeah.
Because, so I'm utilizing the easier one. Z is less than 1.71. That z-score or that area is going to be larger because that z-score is larger. And to be even more helpful, the inequality is in our favor. Z is less than 1.71. That is perfectly formatted for our table in the back. So that one is what I looked at first, because we have the z-score and it's to the left. The other one was not the case because it was Z is, and I'll illustrate that in red. This one over here, Z is greater than 0.86, which means we would be looking at values to the right. But that's not compatible with our table. It only works with to the left. So we had to complement it.
Right.
And when you complement, you're ultimately subtracting it. And so that's why the subtraction gets tacked on the back. Since we subtracted not from 1, because we have more context in this problem, we subtracted from the upper bound in this case. So that's why they ultimately switched. Does anyone have any questions before we look at a percentile problem? So example 7 mentions something about a percentile. It does have the same assumptions as before, a random variable x, not a standard. Well, it does say that the random variable is normally distributed, so it's a normal random variable, not a standard normal variable, which means there will be some conversion that we have to address. But it does say something interesting. Find the 8th percentile. We've heard of percentiles when we talked about when we were talking about the 5-number summary, around that part of the notes. Percentiles refer to what percentage of the data or what boundary expresses a magnitude larger than a certain percentage of the data. So in other words, an 8th percentile means this would be a value that is larger than 8% of the values in total, an 8th percentile. I think the example I gave when we talked about percentiles was when you took the ACT score, they gave you a percentile. If you scored in the 75th percentile, that means you did better than 75% of people who took the test. So what this means, so if you're larger than this value, then all this breaks down to is exactly this. It's saying that the area to the left of whatever your value is 0.08. And the reason I wrote 0.08, that's 8%. So basically the 8th percentile is telling you the area. That's it. It's a fancy way of them telling you the area. It's the area to the left because this is values you are greater than. So basically your value is the upper bound and then you're better than all these other values which are to the left of you. So basically, they're giving us the area. We have to find the data value, not the z-score. I mean, the z-score is going to help us, but we're trying to find the original data value. There's a mean of 68 and a standard deviation of 6. That means we can expect the value to be kind of close to in between the 50s and the 70s to be our answer. So an area of 0.08, we can go and use the table to find the z-score. So actually, I should have wrote z's here. So that's my fault. I should have wrote z's here. Capital Z and then a lowercase z, because we have to go through that conversion. I mean, there's some validity. I guess it wasn't wrong, but I think this is more helpful for the way we're going about these problems. So an area of 0.08, let's just go to the table, see what happens. So 0.08, we look around at the table, and so remember the areas, these are the values inside the table. 0.08, that lands us at really one of these two values. So it's one of these two values. And if I want to get as close to 0.08 as possible, one of these is ever so slightly closer than the other one. That one's only 7 10/100ths or thousandths, 10 hundredths, thousands, 10 thousandths. So it's only 7 10,000ths away, as the other one is 8 10,000ths away. Again, I think my math lab does allow a little bit of flexibility. If you chose this one over to the left, that should be fine. The closest one to 0.8 is the one I circled. And the z-score that this corresponds to, it's negative 1.41. So negative 1.41. That's the z-score we found. But this is not the answer, because it doesn't want the z-score. But the z-score is very helpful. So in other words, notice, if you might have already noticed it, we're kind of working backwards in this problem. Normally, we have the original values, we find the z-score, and then we find the area. But notice what they're having us do here. They give us the area, we find the z-score, and then we're finding the original value. So we're working completely backwards. So the last step is converting the z-score to whatever its original value was, whatever its recorded value was when you went out and you studied that group of people or group of objects, whatever it was, and you got that raw data. You're trying to figure out the original raw data. So the way you convert, well, the general formula, as I've written a few times, I'll write it again. This is the formula to find the z-score. Problem is, we already know the z-score. So let's write in what we know. We know that the z-score is negative 1.41. X is what we're trying to figure out. The mean they gave is 68, and the standard deviation was 6. And yes, that is a little bit of algebra. That is algebra. I'll skip some of the algebra. So negative 1.41, because we don't deal with too much of it in this class. This is probably the most algebra we'll look at. Times 6 plus 68. I'll just go ahead and sum up the algebra. Multiply both sides by the denominator, add to both sides 68. That's high school algebra, or you can just simplify it as this. And so it's just a calculator problem. And this will give you, well, the final answer. Negative 1.41 times 6 plus 68, and this would be the original data value, 0.54. So this would be the value that is higher than exactly 8% of the data values in the study. Does anyone have any questions about this? Which chart in terms of the two tables at the bottom? So really, these are the same chart for the most part. So no, this chart, in fact, it's so large they had to break it up into two. The only difference is that this one has negative z-scores with fairly smaller areas. But if let's say you have a positive z-score, then here's all the positive ones over here. And notice their areas are going to be much larger. So basically, you would use this first chart if you have a negative z-score, or if you have an area that is less than 0.5. Use the other one when you have a positive z-score or an area greater than 0.5. And again, you can always, as far as the area thing goes, if you just kind of look at all of them, so you go down each row, you see they get a little bit larger each row you go down. And you see it goes all the way up to, all right, there's some 0.4s, all the way up to 0.5. And then you could think, oh, okay, well, what do I do now? My area is 0.67. Well, you can keep going, and you can see there's 0.5s, and then 0.6s, 0.8s, and 0.9s, and stuff like that. So is anyone in here a football fan? Anyone a football fan? No one's a football fan. Not one person is a Saints fan in here. This is the worst class I've ever had. I'm just kidding. But, all right, so I was expecting this to be a little bit more topical, but is anyone in here a fan of any major sport? Baseball, hockey? Yeah, no sports? Okay, doesn't matter. Well, as you might know, during these major sporting events, they play commercials, but how many commercials? Wall Street Journal actually took a lot of samples, which would be individual football games, and they determined that they play commercials quite a bit, 63 minutes for a standard game of football, a standard deviation of 7 minutes. So for any football game that you watch, you're going to be exposed to 7 minutes of commercials. 63 minutes of commercials about that area. And so, over an hour of commercials, that's pretty insane. And we're going to figure out, so it's just some application problem we're going to look at. We're going to figure out certain probabilities. So it's basically the same problems as before, but with some context. What's the probability that between 50 and 75 minutes are spent playing commercials? So this is the probability of 50 less than x, less than 75. And notice I'm using x because they told us that this is a normal distribution. So I'm using x, I'm not using z, because we have to convert to z first. So that means we need to convert 50 and 75 to z-scores. And I'll do this down below. So the first one was 50. The mean that they told us was 63 minutes. The standard deviation was 7. And I'll go ahead and do the other value as well, 63. Divided by 7. So let's figure out these very fast. 50 minus 63 is negative 13 divided by 7. Negative 1.86. So that'll be the first one. We can now use a capital Z because we are now referring to z-scores. And so we can figure out the other one as well. 75 minus 63 divided by 7, and that's 1.71. 1.71. So notice, the first thing I had to do, no matter what, was convert to z-scores. This is pretty common whenever you have, or start off with a normal distribution instead of a standard normal one. And now we can use the table. But in particular, the inequality that is most convenient to us and also will give us the larger areas, the one I underlined in blue here. So this is going to be the same as, example 6. Z is less than 1.71, so that's going to be the larger one, because 1.71 is the larger z-score. And then subtract that one off by the complement of what I underlined in red. Because z is greater than implies that, well, we're looking to the right, but we have to complement that, so we can look to the left. So that's why there's a subtraction all of a sudden. So now z is less than, technically less than or equal to, but it means the same thing. Okay. So all we have to do, go to the table, see what these z-scores correspond to in terms of area, we're done. Start with 1.71. 1.71 is a positive z-score, so we'll use that one. So these are negative z-scores. We'll skip all past those. So 1.71, right? 1.71. 1.7 is this row. Just do a few of those because I see that 0.01 is right there. And so that gives us 0.9564. 0.9564. 64. We find the z-score, or the area corresponding to the z-score of negative 1.86. Negative 1.86. So I'll use the negative z-scores. Here's negative 1.8. Go out a few here. So I see that 0.6 is pretty much right here. The overlap is 0.0314. Subtract those two, we're done. So it's 0.925. Well, let's look at another one. Fewer than 50 minutes. So x is less than 50. We need to convert that to a z-score, but we figured that out in part A, actually. So I'm just going to steal that answer. So actually when z is less than, and the z-score corresponding to 50, or if you just compute it again, you'll see that it's negative 1.86. And in fact, we already found this value. So this one's pretty easy because notice we found that value. I just highlighted that one. So again, the equal to sign doesn't do anything. Or you could go find it again. It doesn't matter. Okay. So I guess that's sort of the recycling information you can utilize if you do notice that. Okay. Who here has their tables with them? So you all give a shot at part C. Let's make sure you all know how to do it. All right, if anything, from this point that I have written up here so far, what would you do next? Not yet. Well, not if you want it to be, the number on the graph will not be the correct answer immediately. You have to do
Oh,
something.
you have to, on the correspondent or whatever it's called, because it's greater than.
Yeah, you have to find the complement.
Is the answer 0.7157?
Let's find out. Did anyone else get that? 0.7157? Let's find out. So you have to do 1 minus the probability. So let's figure out where negative 0.43 is right fast. 0.43 seems to be right here. 0.4 was it, right? Negative. What was the z-score? I already forgot. Point negative. All right. Negative 0.43. So 3336. Cool. 0.3336. The difference between those two will be the answer. 3336. I got 0.6664. If you did not get that and want to ask me about it, go ahead and do so. If not, I am out of time. We will continue this on Wednesday. I'll probably push the homework back to Thursday then to give you an extra day. What's that? because, one second.